All right, good evening, good night, good morning, good afternoon, depending on when you're watching this video. In this video, we're going to work through the hypothesis testing exercise given on slide 27 of lecture set 8. So in this exercise, we have experimental determinations of spring constants were made for type 3 springs, which are 6 inches and have a TSC, a theoretical spring constant of 2.63. At the 5% significance level, is there evidence that the long run mean for type 3 springs is less than 2.63? Use the summary statistics for the SRS given below. All right, so as always, we start off with an assumption check. Okay. So our first assumption is that we collected a simple random sample. This is true because we are told that our information is from a simple random sample. Our second assumption is that X bar is normal. All right, in this exercise, we're not given any information about the population from which we are sampling, but we do have a sample size of 50. So we can say that this is true by the central limit theorem. And then our third assumption is sigma known. We don't have sigma. We're not given any population values. So we don't have this value, but that's okay. It just means that this is going to be a t-test. Okay, on step 1, we have to state our null and alternative hypothesis. So we want to test if there's evidence that the long run mean for type 3 springs is less than 2.63. So we have mu equals 2.63 versus the alternative that mu is less than 2.63. All right, and then on step 2, we give our significance level, which is 0.05. And then on step 3, we give our test statistic. So this is t, which is x bar minus mu 0 divided by s over the square root of n. Okay, so our mean is 2.58. Okay, which is minus 2.63 divided by s, which is 0.064 over the square root of 50, which is negative 5.52. All right, now on step 4, we can take either the critical value approach or the p-value approach. So if we take the critical value approach, we would start by sketching out a student t-curve. So something that looks like this, centered at 0. We're conducting a lower tail test. So that means the rejection region is going to be in the lower tail of the distribution. Okay, so down here. And this area is going to be a size 0.05. All right, so that means that our critical value for this test is a negative t on alpha, comma, n minus 1. So this is going to be negative t 0.05, comma, 49, because we have 59 observations. So we go to our student t table. We have 0.05, 49. So our critical value is 1.677, right? Okay, so this is a negative because we're on the negative side of 0. So we just write negative 1.677. Okay? So one of the nice things about the t-table is because of that symmetry, we don't need to worry too much about the positive versus negative in searching for the number. We can just treat everything as a positive, and if it is on the negative side of 0, we can just put a negative in front of the value. All right, our test statistic was 5.52. So you can see that this value here is quite far into the rejection region, which would mean that on step 5, we have evidence to reject H naught. All right, if we take the p-value approach, Okay, we start by sketching out our student t-curve. Okay, and then we mark down where our test statistic is. Okay, and then because it's a lower tail test, the area to the left of the test statistic is going to be our p-value. All right, so here, the p-value is the probability that t is less than negative 5.52. Okay, so we have, as shown above, a degree of freedom equal to 49 because we have 50 observations. So as we previously established, the probability that t is less than a negative is the same as the probability that t is bigger than the positive. So we can go to our student t table. We have 49 degrees of freedom, and we can just treat our test statistic as a positive number. So we're looking for where 5.52 fits in on this degree of freedom line, and it is bigger than 2.680. So 5.52 is bigger than any of the values listed on this line. So that means that the area that we are studying, the area of the p-value, must be less than 0.005. Because you can see that as the numbers get bigger as you move across, the areas get smaller. So if we go back here, we can say, since the probability t is bigger than 5.52 is less than 0.005, then the probability that t is less than negative 5.52 is less than 0.005. Okay. Therefore, the p-value is less than 0.005. Okay, so now on step 5, we can make our decision. So if we took the critical value approach, we would say, since test statistic is in rejection region, reject H0. If we took the p-value approach, we would say, since the p-value is less than alpha, reject H0. Okay. Now here, with the p-value, alpha is equal to 0.05, right? But our p-value is less than 0.005. So the idea is any number that's less than 0.005 must also be less than 0.05. Okay, so the p-value, because it's smaller than 0.005, is automatically smaller than the significance level alpha, because that is 0.05 or a size 0.05, and 0.005 is a smaller number than 0.05. Okay. So then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest that the long run mean of type 3 springs is less than 2.63. So again, with the conclusion, I'm simply just stating what the test has revealed. And in this case, at the level we tested, which is the 5% level, the data gave evidence to reject the null. So this is giving evidence in favor of the alternative. So I'm simply stating that there is evidence that the alternative is true, but I'm phrasing the alternative in the context of the problem. And the alternative is that mu is less than 2.63. So as always, if you have any questions, please let me know.